Thank you for coming, everyone. So my presentation today is about recursive proofs, and it's titled Recursive Proofs for the Rest of Us, by the intention that I'm going to give you an overview of what this technology do, what you can use it for, building your applications here at the hackathon, and a little bit about the different constructions that are out there. I'm going to be focusing more on familiarizing you with the ideas and, the vocabulary. But if you have questions and anybody is curious about the details, we have time for questions at the end, so please do ask questions. Okay, let's get started. Let's start from, reminding you what is this zero-knowledge business about. So meet Alice and Bob. Alice and Bob are two nerds with trust issues. Alice wants to convince Bob that she knows some W, we call it witness most of the time, such that the function f of x of w is equal to some y. Okay, so x, y, f, all of them are public, everybody knows them, but w is hidden. And we want to do two things. Alice wants to make sure w is kept secret, and Bob doesn't have much time. He's a bit dumb and slow, and we have to make the verification as easy as possible. So you already know a lot of applications that use, this technology, like ZK rollups, all of the different games like Dark Forest that use this technology. I'm just setting the terminology for you here. Okay, so we want a few good properties out of these, and we actually can get these properties with constructions that we know and love today. First one is privacy. Okay, again, we call it zero knowledge as well. W must be kept private. You can think about this as, some part of the input or trace of the execution, something like that, is kept private. Sometimes because we really mean to keep it private, sometimes because there is no need to share it. The second part is integrity of the computation. We want to make sure that, if Alice is claiming, I executed this function and this is the result, we can trust Alice's claim if we do the verification. And the last part is we want this, proof to be quick to verify, very short, because again, Bob is slow. In our, real world, most of the time, Bob is the Ethereum mainnet, and Alice is, some big supercomputer or sequencer or prover that generates proofs. Sometimes situation is a little bit different. We get to that too. Okay, I'm going to be using these boxes to show the functions. Like there is a function f inside the purple box, which is the prover, and the inputs go into the function, and y is the output of the function, but we get the proof pi out of the prover. Okay, and this is the first component. This is what Alice executes. So the prover generates a proof pi. Pi is very short. And we also have another component executed by Bob, the component that's supposed to be very cheap and easy to run. We call it the verifier, and it gets, the statement, which is, x and y, and also the proof, and spits out accept or reject, depending on if the proof is satisfying or not. Okay, two important points. The first one is the computation has to be expressed as some sort of circuit. For those of you who have seen it before, it has to be an arithmetic circuit defined over a finite field. Basically, we cannot just write Python code or Solidity code and expect it to be, proved. There might be tools that do this for us, but at some level, it has to be translated into something called an arithmetic circuit. And these arithmetic circuits can do only arithmetics over some finite field. And this is going to be important during the talk, so that's why I'm mentioning it now. In particular, that field is, some called the scalar field of some elliptic curve function. But if you don't know this stuff, this doesn't matter. You can follow the talk, that's fine. The second thing that I want to emphasize is most of the time, the verification of the proofs has an expensive part. Like there is a part that's the bottleneck of verification, okay? And that part, especially on the proofs that we deal with on Ethereum mainnet, are, something called pairing check. Again, we are using this, finite fields that are obtained from some elliptic curves, and some elliptic curves provide this nice thing called pairing. And most of the constructions that are efficient and have, short proof size rely on pairings. And we have to do a pairing check to make sure, the proofs are valid. So the verifier does a pairing check. To think about it conceptually, if this stuff is new for you, the pairing check is just checking some, element A times some constant is equal to another element times another constant. And these, elements A and B belong to some field, okay? This is very simplified version of the pairing check, but this is enough if you want to follow the talk. Great. Now that we are all set, let's get to the recursion business. Okay, so the main topic is recursive proofs, and recursive proofs are basically proofs about other proofs. What does that mean? Imagine we have a computation. Part of this computation is verifying some other proof is correct, and then maybe we have other stuff to do as well. Like maybe we were doing some computation for a while now, and we generated for the a proof for the computation so far. Like maybe it's a computation that takes ages to run. And I'm someone who were, responsible for doing this computation. I worked on this computation for 30 years. And now I want to pass it along to the next person. I have a proof that, okay, this is the proof for the computation so far. This is the result. Now you carry on. And the new person is going to first verify what I have done so far and then keep doing other stuff, right? So in the picture here, I drew a green, rectangle. This is supposed to be the verifier. Remember, we had a verifier function that was, used by Bob, or maybe it's a smart contract at Ethereum mainnet, usually, that verifies the proof is correct, right? So we have a component now that does the verification, but now it's done inside another circuit. Like maybe we executed some other circuit, there is a result, and we created a proof for the execution of that circuit, okay? But this is a bit tricky now because we want to do the verification inside a new circuit, okay? And we do some other computation as well. So to summarize, what does this new proof pi prime says? It says two things. First, it says I know a proof pi for the computation that was done before, like some f, and that proof is accepted by the verifier. Like this green box accepts the proof for the computation so far. And also, I've done some new stuff. Let's call them f prime. And this is the new result, y prime. Okay? So what is good about this thing? The good thing is you can fit more things, like more computation, more data on the same proof. Like imagine you have tons of data. You cannot process it all at once for reasons we're going to talk about. But intuitively, you can think about it like if you have ever-growing data like the Ethereum chain itself, and you want to do some computation about that and prove that computation was correct, you cannot expect it to be, practical as the chain grows and grows and grows. That's just one scenario. And what is the overhead? Like, okay, we want to put more computation and data inside a proof. But what is the cost that we are paying? The cost is overhead of, executing these verifiers. Each time we want to, pass along a proof from someone to someone else and add more stuff to it, we have to incur the overhead of verification of what has been done so far. Let's get a bit deeper into what is good about this stuff. So we can do two main things with this, technology. First one is compression, and the second one is composition. So what do I mean by compression? I mean, taking large proofs and making it small. For instance, Polygon ZK Hermes. How does that work? Inside, they have an efficient proof system in the sense that the prover runs very fast. But it uses a component called Fry. It's a polynomial commitment scheme that's very fast to execute, but it generates humongous, proofs. If you want to post that proof directly on mainnet, you have to pay a lot of money in gas. What they do is that they wrap their proof inside another proof, and then it's short. But this is not specific to them. This is an idea that you can use in many different scenarios. Imagine you have a circuit, if you know about Planck circuits, for instance, and your circuit has many columns. Each column, and the commitment to each column has to be part of the final proof. So the more columns you have, the larger is your proof. But it's easier to design circuits with more columns. So what you can do, you can use as many columns as you want, but then wrap your proof in another final proof that just does the verification of the first proof. And if the verifier circuit is small, meaning that it has few columns, then your final proof is small, which is nice. So this is the first thing we can do with compression. Another thing we can do with compression is more about, the size of the computation or data we are handling. As I mentioned, we can have scenarios in which we have a lot of data or a lot of computation, and circuits are kind of limited in nature. Like they're limited by two things. Maybe you have a computer that has limited memory, which is always the case. Like you have a limited time and you can't do the proof all at once. Like maybe you want to generate a proof for terabytes of data, okay? That's just not possible because, the proof generation process consumes that much, memory. You have to keep all those stuff in memory because you have to generate commitments to this, data and, run FFTs and stuff with the same size. So that's not feasible. And maybe your, data you're talking about is ever growing. It's growing and growing and growing. Like you want to claim something about Ethereum's chain. So the idea here is we break the original computation into steps. One scenario you can, think about, we do this like you want to execute a smart contract and generate a proof for it, a smart proof for it. One way to approach this is to break the execution of the smart contract into opcodes and, recursively execute each opcode and verify the proof for the execution so far and go on like that. Versus looking at all the opcodes all at once and generating a proof all at once. So what is the trade-off here? The trade-off here is basically we trade memory with compute. Like we spend less memory at each step, but we get to spend more time on this and, incur the overhead cost of verification and at each step, right? But sometimes it's just not practical to do it at one go, so we have to do this. Or sometimes maybe we are willing to pay more in compute. One example of this is maybe we want to make a light client, a ZK-enabled light client for Ethereum, or a fast sync for Ethereum. And one thing that we have to do when we sync with network or we create a light client, we have to verify that the blocks are valid, like the content of the block is valid, like the signatures are valid, the execution is valid, stuff like that. And one approach is for each block, we send the proof that the block was executed correctly and everything inside the block is valid. But we can go one step further, and that's generating a proof for the whole chain up until some point that the whole chain is valid. Suppose we want to do this. If we recreate the proof for the whole chain whenever we have a new block, it's going to be very painful and costly. But if you use this recursion technique, we just verify the proof up until the last block, prove the new block, and now we have a proof for the whole thing again. The second item is more fun and more relevant to building dApps and games and stuff like that. So pay attention. So what does composition mean? It means that the prover is going to show knowledge of something that he doesn't really know. More precisely, instead of proving that, okay, there is some W that I know, but I'm not sharing with you, that has this nice property, claiming that somebody else knows a W that they didn't share with me, but it's correct, like it satisfies some, stuff, and I'm going to claim more things about that. I'm going to give you an example, and it's going to become clear. Think about the partial information games, like poker. When you're playing poker, let me go one step back. Think about partial information games. And by partial information game, I mean any game that, some player knows something that others don't know. Like there is something about the state of the game that only I know. There is something about the state of the game that only you know, like many games, like poker, Counter-Strike, whatever. You don't know where I am in the map when we are playing Counter-Strike, or you are not supposed to know at least. When we are implementing these games in a decentralized fashion, it gets tricky really quick because we want to enforce that players, change the state of the game correctly. Like if we are implementing Counter-Strike in a decentralized fashion, you don't want to let me jump from one place in the map to another place. You want to make sure I'm taking steps, right? But on the other hand, you don't want me revealing where I am in the map, okay? So there is a simple trick, like I hash where I am in the map, and each time I take a step, I open the hash as a witness, like in the circuit as this W, hidden W, and then take a step, update the pre-image, and take a new hash and give you the new hash, something like that. It's easy to do, but it entails recursive probes because each time you have to verify the proof of the previous hash I give you, and then I have to verify the proof of previous hash I give you and then update it, something like that. This is the case when you're dealing with any partial information game, and many games, like many massive multiplayer online games, like Dark Forest, a poker implementation, decentralized, Counter-Strike, serverless, decentralized. All these games involve this. So this is a very powerful tool. Another example, which is, very practical, is, about Zcash. So Zcash enables people transacting without revealing who they are sending the money to and who they got the money from, stuff like that. So abstractly think about that. If you want to enable that on a rollup, what should we do? So basically the goal is the rollup operator is not going to be able to tell who's sending money to whom, right? So it entails two steps. If you're doing a transaction, you have to create a proof for correctness of your transaction, that you're changing the state of the chain correctly without revealing the addresses involved. And you send that proof to the rollup operator. We still want to get the scalability stuff, right? So the rollup operator is going to recursively verify all these proofs and create new proofs that, okay, there's a block. There are these transactions that are proofs. They're not, normal Ethereum transactions. I verified all of them and they are correct. And this is the new state. And this is something that you might have heard about. It's called ZK rollup. Basically having a Zcash as a rollup in Ethereum. And the applications are, endless. If you start thinking about social applications, like there is this one called ETHDOS that gives you the distance you have from Vitalik without revealing the social tree. Like if I'm 5 steps away from Vitalik and I know you, I can give you a proof that you are 6 steps away from Vitalik. But you don't get to know what is my path to Vitalik or what's the social structure here and stuff like that. And how we do that, we first verify that my proof is correct and then add a proof that, okay, I attest that you are my friend, something like that. Again, it's a very powerful primitive. Okay. Now we know we reviewed what are snark proofs. We talked about, what is recursive proofs, what are recursive proofs and why we care about them. Now I want to talk about constructions with you. And this part is intended to be, very newcomer friendly. So I hope I can give you at least a little bit of idea what's going on behind the scene. So the most naive way to do this stuff is the way I was describing so far. And that's implementing a verifier in circuit. Like we have a verifier function. It was supposed to be implemented in Solidity, maybe on mainnet, or in code like Rust or Python or whatever. Let's implement that as a circuit. Let's arithmetize that and put it inside the circuit. Maybe we have other stuff in the circuit as well, but that's part of the circuit. And voila, we have a, recursive, we have enough technology to do recursive proofs, because now verifier verifies whatever we have and we can do more stuff. So this is very architecturally simple, clearly, because it's easy to understand, easy to analyze in terms of security. The problem is it's very costly. The overhead is a lot, especially if we do it naively. And I'm going to tell you why is that. There are two reasons for this, large overhead. The first one is we have to deal with something called non-native arithmetics, non-native field arithmetics. And the second one is often we have to do this pairing check I mentioned at the beginning in circuit, which is a very costly operation. So what is non-native arithmetics in one slide? So elliptic curves, they're defined over two, finite fields. First one is base field, normally shown as FP, and the other one is a scalar field, normally shown as FQ. You can think about this, finite fields as doing regular math operations modulo P and Q, like FP is mod P, FQ is mod Q. Yeah, in the simple case. And the thing is, when we are doing the arithmetic operations inside the circuit, we're doing those operations over FQ. So everything is done mod Q, okay? But the proofs are mod P, like they live in FP. And if we want to argue about proofs inside the circuit, then we have to do arithmetics over FP, but using FQ elements. So you see, you have to do some simulations. Like it's like when you implement big num in C++ or stuff like that. You have to do some things like breaking the stuff into limbs and doing the multiplications very carefully, doing the carry and stuff like that. So even arithmetics becomes non-trivial. So for that reason, we call it a non-native arithmetics, because we have to do arithmetic over certain field, but we get to have access to another field. Okay, so that adds a little bit of overhead. But there are tools out there that help you to do it. You don't have to implement it. Like if you're using Circom, there is a Circom pairing library and Circom big int library. And if you're using Halo 2, there is Rung Halo 2. So there are tools available for you to do it. The second, an idea, to get away from doing this, non-native stuff is using something called cycle of elliptic curves. So you don't have to use the same elliptic curve each time you're generating a proof. You can switch your elliptic curve from time to time. And the idea is if you have a curve with parameters P and Q, like the base field is P and the scalar field is Q. If you have another field with alternating parameters like Q and P, then each time you want to talk about something in FP, you just alternate to that curve. And one of the main contributions of Zcash people is creating a pairing-friendly cycle of elliptic curves called Palace and Vista. The problem is we cannot use that on Ethereum, because on Ethereum we only have this one curve called BN254, and BN254 is the only curve that's supported as a precompiled. Other curves, if you want to do them, we have to implement the Solidity code, and that's very costly. It's not worth it. But the problem is people proven mathematically that there is no efficient pairing-friendly, cycle of elliptic curves for BN254. So there's no hope. This approach is that's going to work for us on Ethereum. I have two more, ideas, which are, based off the works that came out in the last 2 years. The first one is something called proof accumulation. So we want to do some recursion. Maybe we want to do 100 steps of recursion. Prove something, recurse on it, recurse on it, recurse on it. And at the very end, we want to post the final proof on mainnet to be verified by some smart contract, okay? The core idea is maybe we delay the hard work to the very end. And remember, what was the hard work? It was this pairing check stuff, right? And if we do that, and if we do recursion for many steps, many iterations, we kind of get to amortize the cost stuff, that one-time heavy cost over all the steps, and kind of it makes sense now. So the idea is we accumulate proofs, which I'm going to hint at a little bit in the next slide. So we accumulate proofs somehow combine all the proofs, okay? And we verify that this accumulation is done correctly. So we have to do some verification in circuit, but it's not a full snark verification. It's just a verification that the accumulation is done correctly. So the verification is much smaller now, like maybe just 10-20% of the original the cost of verifying the whole snark, okay? And on top of that, we never do the hard work in circuit. Like I told you, at the very end, we have to do this pairing check, but we do it in a smart contract on Elbow. So it never happens, the hard work never happens in circuit, which is very nice. So I'm going to quickly go over this slide because we don't have time. So the idea is we use this trick called random linear combinations. We combine all the, pairing checks with random coefficients, and then just do the pairing check for the combination of all of them. And you can prove that very high probability if the final one checks out, all of them would have checked out. The other idea is statement folding. This one is a little bit different in the sense that it happens a little bit sooner in the life cycle of the proofs. In accumulation, we have to generate proofs for each step and then we accumulate, right? But in statement folding, the idea is we don't even generate the proofs. At the level of statements, we accumulate the statements, and then we get to generate a full proof when we accumulated all the statements, okay? So the core idea is very similar. We want to delay the hard work as much as possible, but because we do it a bit earlier in the life cycle of the proofs, we get to do more saving. And this is very new. Like these ideas came out maybe mid 2022. So this is very new. And yep, this is my final slide. So basically, in circuit verifiers, proofs live their full life cycle and we pay all the cost. Accumulation schemes, we get to avoid the verification until very end. And statement folding, we don't generate the proofs at all. Like we do generate some proofs, but generate full proofs at all until we accumulate, we folded all the statements. So that's all what you can do now. So I want to encourage you to use these ideas of recursive proofs. Think about them, come up with ideas how you can make partial information games, social applications that somehow exploit this power of recursive proofs. The other thing you can do, many of these ideas came out very recently, and there are not good implementations, or some of them don't have any implementation. So you can go out there and find which one you like more and start contributing to them. And the last item is there's a lot more to learn here. I'm happy to talk to any of you if you want to pointers to more resources, and learn and just educate others. Thanks a lot.
There's any classes to maybe libraries or things for Jahanara's
Yeah. So there are certainly many tools. In particular, I mentioned circumpairing and circumbigint and Rank Halo 2. These are libraries that you can use to implement in-circuit verifiers or in-circuit, accumulation verifiers or folding verifiers, stuff like that. But there are tools that, do the whole process for you. But on the top of my mind, I don't have them, but please talk to me later. Yeah. Oh, yeah, absolutely. Yeah. Yeah, that's a very good question. So the way we generate the proofs is that we most of the time use KZG commitments. And KZG commitments works like this: like we take something and put it in exponent, like in the elliptic curves. And when we do that, we move from a group to another group, one field to another field. So the commitments are, in this other field, that's why, the elliptic curve points are pairs of points on base field, like FP, and you have to deal with them when you're dealing with the proof. So that's why, and you can't really get away from that. Like that's part of every construction.